Alrighty, so today we're going to almost finish this chapter. We're going to come real close to it. So don't forget, there's mastering due tonight. And then I know you're going to be thinking 3-day weekend, but when you get back, Monday, there's homework that night. So there's no homework on Friday because I thought that'd be mean. But there is homework right when you get back, so don't forget to do it. Yes, and then next Wednesday. Alright, so where we left off, we talked about... Let's go back and find it. Alright, heat transfer. Right, we talked about heat transfer and freezing, exothermic, and the entropy of the universe is related to the entropy of the system and the surroundings. But, right, temperature is a big factor in entropy. And so the higher the temperature, the lower the magnitude of delta S surroundings, like we talked about on Monday. So combining the two ideas of heat transfer and temperature effects, we end up with the equation delta S surroundings is equal to, what's little q stand for? Heat, right? So delta S surroundings was directly proportional to heat, and it's indirectly proportional to temperature. So this equation combines those facts together. I realize this is a stretch of a sentence. Remembering how enthalpy works. Vaguely remembering the idea of enthalpy. Heat. At constant pressure, we change this little q to a delta H. Which means now I have an equation that directly relates enthalpy and entropy. Why would I need to have that negative sign in there? If I have a, what sign does delta S have to be spontaneous? Positive, right? And exothermics are usually considered spontaneous, so what sign does exothermic H's have? Negative, right? So to make the signs line up, they have to be opposite signs. Alright, so we have this brand new set of equations. Let's do some practice problems and kind of figure out how we use them correctly. Alright, so consider this combustion reaction below. I have propane and oxygen reacting together to make carbon dioxide and water, and you're given the delta H of the reaction. Is this delta H exothermic, endothermic, or you have no idea? Exothermic. How do you know it's exothermic? It has a negative sign. Okay, excellent. First thing I want to do is use my new equation to calculate the delta S of surroundings if I'm at 25. Here the PowerPoint looks like 250. So let's see, 25 superscript degrees Celsius. Alright, so alright, what is is the thing we have to do before we can even start solving the problem? Convert to Kelvin, because everything, enthalpy, entropy, everything in this chapter is Kelvin. Anytime you see thermodynamics, it's in Kelvin. So how do I convert 25 degrees Celsius to Kelvin? Okay, good. So now, delta H will always be in kilojoules. S depends. Usually in joules, but in this case we can leave it in kilojoules. Let's do that. How many significant figures do I get? Unfortunately, we're going to go back to remembering significant figure rules in general. Alright, so that's part A. Is the delta S surroundings increasing or decreasing in entropy? Increasing, right? It's a positive value, so it's becoming more entropic. More entropy. Alright, so that's delta S surroundings. Alright, delta S is a system. What is the system in this case? No. So if you're picturing in your head how to figure out what the system is versus the surroundings, it's the reaction. The reaction itself is the system. Alright, so delta S of the system, or delta S of the actual combustion reaction. Are we changing states of matter? Oh, that should be a gas. The answer to that should be no. That's why it's a trick question. Alright, there we go. Are we changing states of matter? No. Okay, we're supposed to not change states of matter, it's supposed to be vapor. Alright, how many moles of gas total are reactants? 6. How many moles of gas total do I get out of it? Is that increasing or decreasing entropy? It is increasing, right? I had 6 slots and now I have 7 slots. So I've increased the entropy. What is the sign of increasing entropy? That's it, positive. Right. Alright, so then let's look at so this is my equation for delta S of the universe. Right, we've had that before. Right, so it's just in the systems plus surroundings. What is going to be the overall sign then of my delta S of the universe? Positive, right? Because I have a positive thing and a positive thing. This is a positive value. So what would you say about the entropy of this reaction? Is it increasing or decreasing? Increasing, so is it likely to be spontaneous? Yes. So positive, likely, spontaneous. Both parts of it. Yes. Right, because enthalpy is not enough to tell us the whole story. Let's see both. Good? Thinking through that? Okay, good. Alright, let's do another one. Alright, so for a unknown reaction, I gave you the delta S, I gave you the delta H is negative 125 kilojoules, and the delta S of the reaction is 253 joules per Kelvin. As long as you're at 25 degrees Celsius, I want to figure out the delta S of the entire universe for this reaction. Not really the delta S, the entire universe. That's a separate question. Alright, so right here is my and oftentimes delta S reaction, delta S of system are used interchangeably, right? Because the system is the reaction that you're looking at. So they mean the same thing. Alright, so I have this already. That's given. How do I figure out the delta S of the surroundings? The one we just had, right? Alright, so we're just going to plug it in. What is that? Something like that. Okay, so now I want to go plug this in. What is going to be my issue when I go to add these together? Those pesky units. Right, because I have my surroundings in kilojoules, but my system's in joules. Preferences, which way you want to go with it? All kilojoules? All joules? All joules? Okay. Did everybody mostly get that? Yeah. Is this reaction spontaneous as given the information? Is it a spontaneous reaction? Yes, how do you know that? It's positive, right? The delta S of the universe is positive, therefore whatever this mysterious reaction is. I stand pick one. It is spontaneous. Good, good, good. Questions about using those two parts together, figuring out the overall delta S? Alright. Well, that's all handy and good. Is everyone done with the sheet? Okay. Alright, so now, right, this is the equation we just had. Delta S of the universe, system, that's really surroundings. That is handy, but it's often difficult to determine these individual parts. The delta S of the universe, H system, S surroundings, all those things. So we rearrange it into a more user-friendly version of the reaction, where if I take this delta T, right, because no one likes fractions, I change it to delta T Alright, multiply everything through by delta T. And I have everything in terms of systems on this side, and how the universe is affected by temperature on that side. This right here is known as delta G. Which brings us to everybody, like the one thing everybody remembers from high school thermodynamics is when you get to the equation right? That's like the one equation everybody remembers from thermodynamics. The Gibbs free energy equation? No? Okay. In that case, yay, it is the Gibbs free energy equation. For those of you who are NCIS fans, this should help you remember which equation this is. It is the Gibbs equation. Although it won't hit you on the back of the head. Although I might if you forget it. Which, if you watch NCIS, that's hilarious. If you don't, then never mind. Alright, so what is the big deal about this Gibbs free energy, and why is it useful, and why is it a better thing to use than this combination up here? Alright, so the change in Gibbs free energy, I realize I might move that too fast. There we go. Alright, the change in Gibbs free energy for a given process occurring at constant temperature and constant pressure, right, is proportional to the negative of the delta S of the universe, just like it was up here, right? So since the delta S of the universe, its main purpose is to tell us whether or not a reaction is spontaneous. Delta G tells us similar information. Alright, so delta G is proportional to the negative delta S of the universe. Right, meaning that they're of similar magnitude. Alright, what sign does delta S of the universe have if it's spontaneous? Positive. If delta G is proportional to the negative delta S of the universe, what should delta G be to be spontaneous? Negative. Yeah. So since they're equal but opposite signs, you'd have a negative delta G to be a spontaneous reaction. Or the opposite true. If delta G is positive, then that is a non-spontaneous reaction. Proportional, it's the same as that part of the sentence, but fish with no closed-in tail and mass means proportional. This little symbol-y thing. They're equal values but opposite signs, kind of. And the thing is that delta G is going to depend on enthalpy and entropy and temperature. So it combines all the things we've been thinking about into one super equation. It's like the Voltron equations, right? Individually, they're good, but altogether, they're much better. No, nothing. Okay. There's no other cartoons, I think, that combine like that. Yeah, no, I can't think of any. We'll watch a clip of Voltron next time. That way, that analogy will make a lot more sense. Nope, okay. Okay, these terms are related, but how are they related? Excellent question. I'm glad you asked it. Let's talk about how delta G depends on H, S, and T. Alright, so let's look at some case scenarios and we'll see how delta G works out depending on what other factors I know. Let's say, we'll start with the softball, we'll say delta H Alright, so let's say I have the reaction where I know delta H is exothermic and delta S is increasing entropy. What sign would delta H have? Okay. What sign then should delta S have? Okay. Alright, so looking at my Gibbs free energy equation, if this is negative and that is positive, what is going to be the sign of delta G in this scenario? It does not depend on the temperature. It's going to be negative at all temperatures. Now it's going to come down to the units, really, right? So in the previous one we just did, what was delta H in units of? You may want to take 2 seconds to flip back, right? Delta H is always going to be in kilojoules, and S will always be in joules. So S will always be much smaller than H. And so H is really the dominating factor in a lot of these problems. Just because, I mean, it's a factor of 1,000 bigger than S. Alright, so if you have an exothermic reaction with increasing entropy, should that be non-spontaneous or spontaneous all the time? Spontaneous, right? You already know that. Exothermic and increasing entropy, those are like the two things that are always spontaneous. So always spontaneous combining together makes always spontaneous. Okay? Let's do the opposite case then. Alright, so if I have an endothermic reaction and decreasing entropy, off the bat, if it's endothermic, is that typically spontaneous? No. If I decrease the entropy, is that typically spontaneous? No. So if I combine them together into my Gibbs free energy equation, what is going to be the overall sign of delta G most likely? It'll always, yes. So if you have this combination of things, it'll always be positive. If you have that combination of things, it'll always be negative. So then the question is, what if it's not exothermic and increasing, or it's not endo and decreasing, or if it's some sort of combination of that? Then we go back to what you guys originally said. If it is some So if it's some combination of delta H, delta S not listed above, right? So maybe endo but increasing, or maybe exo and decreasing, some sort of combination like that. Then it's going to depend on the temperature that the reaction is taking place at. So, because I can't go through, I mean, I could go through all the scenarios, but we have more exciting things to do later today. In your handout, temperature reaction. Here are all your options. Predicting whether or not a reaction will be spontaneous. Alright, so here's the one we just did. Exo, positive, negative, positive, spontaneous under all conditions. Endo, in more order, non-spontaneous all the time. And these are the two. It's going to depend on the temperature. If it's exothermic, but a delta S that's negative, you got to lower the temperature. If it's endo and positive delta S, then it's going to be positive. You have to raise the temperature to get it to work. So let's do a practice problem where then we can figure out what the correct combination of things is. That's just a handy sheet. You may just want, if you don't print out your PowerPoints normally, you may want to at least print this one out because it's handy to have around, especially for the homework. And alright. Let's say I have this reaction. Methane and hydrogen gas combining together to make C2H6, given delta H is negative 137.5 kilojoules and delta S is negative 120.5 joules per Kelvin. Let's find delta G and then talk about temperature effects. Alright, so before I even go plugging things in, what is the first thing I have to do in order to make this equation work? Convert my temperature. Alright, so this is really 298 Kelvin. And then what is the other thing you see off the bat that you're going to have to fix before the units work out? Joules and kilojoules. I prefer working in joules all the time. But I mean, if you prefer kilojoules, that's fine too. I just like joules better because, right, if I have negative 137.5 kilojoules, if I just add that times 10 to the third at the end, I'm instantly in joules. Instajoules, that's right, we should patent that. Instajoules. Alright, ballpark, yeah. Yep. Alright, so if I get a delta G of negative 1.02 times 10 to the 5th joules, it is super spontaneous, right? Which should make sense because look at this delta H. It's gigantic, right? 6 orders of magnitude bigger, well, 3 orders of magnitude bigger than my delta S. Alright, so if this reaction is spontaneous, let's talk about how the temperature affects it. Oh. That only affects the delta S. So looking at going from 2 moles to 1 mole is why this delta S is negative. But it is so exothermic that overcomes the fact that this is not a favorable entropy. I mean, these two? It really means, thinking organic chemistry-wise, right, this is a whole bunch of double bonds ready to be hydrogenated to make a whole bunch of single bonds. it would prefer that. But, alright, so then the question is, how does temperature affect delta G? Alright, so let's go back to our cheat sheet. Which of the scenarios are we currently in? 1, 2, 3, or 4? Nothing. 2, right? We're in 2, right? Because that's exothermic, and that's delta S less than 0. So, the colder this reaction gets, the more likely it is to go forward. Why would that be? What would happen to this delta T, or this T, as the temperature goes from 298 down to 200? What happens to this side of the equation? It gets smaller, right? So if this side gets smaller, what happens to this end value? It gets even bigger, right? So that's the kind of things you're going to be thinking about. Right, so if I was somehow able to do this at, I don't even know a good answer. 2, yeah, I can't do it 0 because that's crazy, that's 0 Kelvin. If it was like 100 Kelvin, right, it would, in theory, be even more spontaneous than it is currently. Yeah. That's it. Good. I mean, exothermic is good, but it's not good entropy. But the exothermic is so much bigger than this that overall delta G is negative. And anytime delta G is negative, spontaneous. Let's do another practice one. Yeah, it looks like a 0. That's oxygen. Now it looks like an eyeball. Okay, 2 calcium solids reacting with oxygen to make 2 calcium oxides. First of all, looking at this, does it make sense that the delta S is negative? Yeah, right? I'm forcing a gas to become a solid. That's not. And I'm going from 3 moles of things down to 2 moles, so it's definitely that. If the delta H is negative, is that exothermic or endothermic? Exothermic, right? So let's figure out what the overall delta G is, and then figure out, is it spontaneous? Alright, so again we're just going to plug it in. Would you consider this reaction spontaneous? Yes. What's the only thing that tells you it's spontaneous in my delta G value? Right, it's negative. Negative. At this temperature. So even though it looks bad, right, going from a solid gas combination, forcing them all together to make a solid, it is so exothermic that overcomes the fact that the entropy is not particularly good. Alright, so those are all the scenarios where I gave you all the information about the H's and the S's and the temperatures. What if you're interested in a reaction that you may not know the delta H of the reaction or the delta S of the reaction? Can you find it? Yes, you can. Okay. I feel like a car salesman. Yes. Yes, you can. Alright. Is everyone done with this? Okay. Alright, so let's talk about... Nobody asked me any questions about it. Sometimes that pops up. Here, right, I have this weird little circly thing up here. All of these circly things. Nobody had any questions about it. I'm assuming that's because you remember that the little circly thing is when I'm at standard state. I'm assuming everybody just remembered that and you didn't have a question about it. That's what it was. Not that you were ignoring it. It's just you're like, oh, standard state, we're fine. Alright, so as a reminder, in case that was not you, this circle, it looks like a degree sign. This side is when the reactants and the products are in what's considered their standard state. Alright, so what is the standard state of our states of matter? Alright, so right there's gas, liquid, solid, aqueous solution. Alright, so if I'm talking about a gas, what pressure do you instantly think of as normal for gas? 1 atmosphere. So that's what gas is. It is a pure gas at 1 atmosphere. And by pure gas, I mean in its elemental-ish form. So like oxygen, or neon, or, I don't know what's another gas, nitrogen. CO2, that'd be great too. Right? Those are all gases in their plain, pure, ordinary form at 1 atmosphere. Alright, if I'm thinking about a liquid, what temperature do we consider normal liquid temperature? 25 degrees Celsius. I'll just go ahead and put it in Kelvin. What pressure should a ordinary boring liquid be at? 1 atmosphere. It also has to be a pure, we're going to call it substance, because it could be a molecule, right, like water, or it could be a pure element, like mercury, right? That's an element, that's a liquid at room temperature and regular old atmospheres. Alright, for a solid, it's the exact same as a liquid. Right, so it could be a piece of iron metal, or it could be a cube of salt. Whatever it is, it's a pure substance at room temperature and room atmosphere. The only one we haven't talked about at all, that we're going to be able to talk about now because we're experts, is aqueous solutions. So if it's aqueous, what is the solvent? Water. So this only applies to water things with water. Alright, what temperature do we typically consider aqueous solutions to be at? Alright, same thing. What pressure should it be at? Good. And this is the new part. It's considered a 1 molar solution. So within its standard state, we consider it a 1 mole per liter solution. Alright, those are all things about delta H's standard state. Delta H is what sort of function? Also starts with an S. The state function, right? State function. Delta S is also a state function. Which means its standard state entropy of a given reaction is the standard state entropy of the product minus the standard state entropy of the reactant. Just like it is for delta H. Alright, so delta H1 we've had before. Oh, so important. Because it's always product monitored reactants, because these are all standard state functions. And so, because we can calculate S, products and reactants, only at their standard state. If they're not standard state, then you don't know this value, so then you can't find delta, and then catastrophe. So it's all downhill from there. So those are experimentally determined, and so I was just giving you those. Right, if you haven't, so let's say, we'll go back to this one, right? So looking at calcium solid and oxygen gas. Is there any way I could really squish calcium solid together with oxygen gas to form calcium oxide at room temperature and room pressure? Probably not. There's zero chance it's going to happen. But we know it's spontaneous at 25 degrees Celsius. It's because this is the net equation. In reality, there's a bunch of steps, like calcium does a little something, oxygen does something, and then overall, it doesn't matter how many steps are in the middle, because it's just final minus initial. So we can only use we use these to kind of get through all those intermediate steps that don't affect the outcome. Alright, so we are now ready to talk about the third and final law of thermodynamics. Take that back. There's actually a fourth law. That's called the zero law. I'm not really going to talk about it much. Okay. So the third law of thermodynamics talks about entropy specifically. So, remember, from whenever you took Chem 108, that's delta H standard state. Then remember what the little f means? Formation. That the delta H standard state formation for an element in its standard state is 0. Sounds vaguely familiar, maybe. Right? So we talked about, if you went to the back of your textbook and you looked up delta H0F of different elements, you could have, or element molecule. Right, if I was looking that up in the back of the book, if I had oxygen gas at 1 atmosphere, 25 degrees Celsius, is that standard state? Alright, what if I had water, 25 degrees Celsius, 1 atmosphere? Also 0. Right, so we had all these standard things. We said the heats of formation is 0 just because we need some place to start measuring from. That's fine for delta H's, but entropy is super temperature dependent, so we can't just use the fact that elements should be 0. We have to define the third law of thermodynamics. We have a measuring point from where we can look at, is it increasing entropy or decreasing entropy? So if you were thinking of the state of matter that has the least entropy, what state of matter has the least amount of entropy? Solid. Excellent. If you were thinking of the coldest temperature that exists on planet Earth, what temperature would that be? 0 Kelvin. So where should I look at a molecule to find where it's the absolute least entropy? A solid at 0 degrees Kelvin. So that's what the third law of thermodynamics states. The entropy of a perfect crystal of a molecule element either way. At 0 degrees Kelvin is equal to 0. Right, because you have to be able to figure out, is it getting more entropic? And so you have to have a measuring, you have to have a 0 spot to start measuring from. And that gives you the 0, right? So like imagine you're using a ruler. If there wasn't a 0 marked on the ruler, you wouldn't know where to start. You can measure a difference, but it wouldn't be an exact distance. You have to figure out in your head where 0 is. And this is obviously theoretical because no one's actually gotten down to 0 Kelvin, and no one's done this, but this is just, we're close. We're close to 0 Kelvin. Like within like few tenths of hundredths of degrees of 0 Kelvin, but not actually there yet. Alright, I'll stop there because the next practice problem will take too long. So, I guess I will see you on Monday to finish this chapter.
Should we have 18 turned out for Monday? Or?
Yes. Yep. Because I think we'll get through these last bunch of problems.